So the third part of the basics of probability is the definitions of probability that philosophers argue over. And we're going to talk about two of them that are very common in statistics these days. The first one, and I did it again. The first one, I like to think of it as being related to the law of large numbers. And it's a definition that frequentist statisticians use. The law of large numbers is talking about how the frequentist definition of probability depends on the long-term proportion of times an outcome occurs when a random process is running. So you run the random process a practically infinite number of times. You count what proportion of the time your outcome that you're interested in occurs, and that proportion is what you think of the probability of that outcome being. So that works with flipping a coin, and the idea is that, so the actual, a better, closer statement of the law of large numbers would be that as the number of trials increases, the observed proportion of times that an outcome occurs will get closer and closer to that outcome's probability of occurring. And so that would look like something like this, where if you flip a coin 100 times, which I did with the computer, you get a track like this. This first time it came up heads, and then second time was tails, and then we had a couple more tails in a row, so now the proportion of heads was lower, and then gradually it gets closer and closer, and now it's sort of bouncing around 50% because it was a fair coin. So the first time the portion is either 0 or 1 because only a single outcome has been observed. But as you increase the sample size, it gets closer and closer to the true probability. So that's what a frequentist, that's why it's called a frequentist, because you have to have a frequent number of flips. It's the long-term frequency of the outcome. There's another definition, though, that is increasingly popular because it makes things make more intuitive sense. However, it turns out the math was so hard that for many years no one used this. But recently computers have become so fast that they have been gaining traction. And so that is the degree of belief definition of probability. And the people that use this definition are called Bayesian statisticians because they use Bayes' theorem to talk about the probability of things happening. And we will talk more about Bayes' theorem later. But the basic idea is that probability is a degree of belief. So it's how strongly or weakly you expect the next time a specific outcome to occur the next time a random process happens. So it sounds kind of squishy, right? Like it's someone's opinion, and yet they're basing all of probability on that. It turns out, though, that if you take for granted the person's rational, like if they're trying to bet on a horse race or something and have a good chance of winning, then that constrains the mathematics of what they believe, so that they're not going to believe that like a bear is going to win the horse race if there's only horses, right? So that, for example, that's a stupid sounding example, but it's actually serious. Like your outcomes are limited to the ones that are possible, and that's a start. And then of the possible outcomes, the ones that you think are more likely to occur have higher probabilities and less likely to occur have lower probabilities. So the things that are intermediate, they're probably intermediate. So that's actually kind of intuitively how we think of probability, because for example, if you are looking for a planet, if you think there might be a 10th planet, for example, it's either there or it's not, right? It's not there part of the time. There's not a long-term frequency. There's either 10 planet or not. So a frequentist would say, well, the probability is either 0 or 1. That's it. There's no other way. But a Bayesian would say, well, we don't know for sure, but based on our evidence, we'd say we think there's like an 80% chance that there's a planet X because of this and this reason. Or they might say there's a 1% chance because of this and that reason. So that actually jives better with how we think about probability.